All right, let's get started. I uploaded homework 2, so I didn't send an email yet. I should. Yeah, I should have sent that. But the homework 2 is up, and yeah, you'll probably have a few weeks to do that. Yeah, if I remember correctly, so the due date should be 13th of March. Okay, and so I'll upload the solution probably next week, and you cannot do all of them yet, right? I think some problems, so it covers chapter 3, 4, 5, and some of the problems in chapter 5 are not ready yet. So yeah, but whatever left is not very hard. You can probably learn on your own if you want. So just an algorithm. Okay, great. Yeah, let's see what we cover in our last lecture. Yeah. Yeah, that'll be, I think that's great. Okay, so yeah, date is wrong here. So last lecture should be 23rd. All right, so in the last lecture, we talked about the fixed to variable length code, and we talked about the uniquely decodable and the prefix code, right? And then we cover the Kraft inequality, right? Which is the requirement of the existence for a prefix code. Okay, today we're going to cover something very similar here, but it's a bit different. Right, so yeah, this is a theorem for the fixed to variable length code, right? So we proved this theorem like 2 lectures ago. Okay, so basically here we show that when n goes infinity, then so basically the average length of a code is basically less than entropy, right? So here we need to be very careful on what the meaning of ln here, right? So ln is the length of the code for a fixed to variable length code. Okay, so basically this n means the length of the block, right, of the source symbols. Okay, so yeah, this is very, very important. And the other thing is that the proof idea for this is that we use the typical set for the typical set and non-typical set to code them separately for the achievability, right? So here, note that, so we have an upper bound here, right? So in source coding problem or in compression problem, upper bound meaning something that is achievable, right? We need to show this is achievable, right? Lower bound is a converse, right? It's an impossibility. Okay, so yeah, and then we define so the uniquely decodable code and the prefix code, right? So in order to define a uniquely decodable code, so basically we need to introduce the concept of the extension code. Okay, so basically what it means is that we concatenate the code all together, right? And then so if for this code it's a non-singular code, right? Then we say it's uniquely decodable, right? And this definition is a definition of the case extension code. Okay, so we just extend the source symbol k times, right? So before, for the length of a block is n, right? Now we extended k times, right? But what we do here is that we encode them separately, right? Like this. Okay, so it's just like, we concatenate the codes all together. Okay, so that's the definition of all extendable code. Okay, so we say so this code is called uniquely decodable if the extension code is non-singular. Okay, so basically it means that if the extension code, all extension code, right? We use C star here. Star basically means that we consider all the k here, right? So if all the extension code is non-singular, it has a 1-to-1 mapping. So basically it means that it is uniquely decodable. Does that make sense? Right? So there's no ambiguity basically. All right, so if you agree on that, then we introduce the definition of the prefix code, right? So definition of that is very straightforward. It's just like know any code word that is a prefix of another code word, right? Okay, and we have a theorem. We say the prefix code are uniquely decodable, right? So yeah, you can check out the proof that we did in our last lecture. All right, and then we introduce the Kraft inequality. Right here, for simplicity, we just consider the coding alphabet only includes 0 and 1s, right? And then basically we can show this inequality holds. Okay, and this is tight, right? So this is a sufficient and necessary condition, right? If we show this is true, right, if it is a prefix code, then this has to be true. And if this is true, we can always construct a prefix code. Okay, the way to construct it is kind of straightforward. We just use the coding tree to construct it, okay, as we did in our last lecture. Okay, but in general, if it's not true, right, so the construction, may not be trivial. So we're going to talk about that later. Okay, and so this is where we left in our last lecture. Okay, so let's see what we're going to cover for today. Today is our lecture number 19. So our agenda today is that first one. So we're going to, let's see this part, whether this part is in the Kraft inequality or not. So yeah, I see. So we're going to continue talking about the Kraft inequality. And then we'll talk about the so-called optimal code. Okay. Yeah, this optimal basically means the converse, right? So what's the best we can achieve for the lossless source code, right? Remember, so we kind of showed that before, but that is for epsilon error, right? But here we show that it's for 0 error. Okay, so that's the difference. And after that, yeah, probably we're not going to have any time. So yeah, hopefully we can finish these two topics. Okay, yeah, let's get started. Yeah, the first one, so for the Kraft inequality, last lecture we show for the prefix code, and then the Kraft inequality has to be satisfied, right? So now we consider a more general case, right? So we consider a uniquely decodable code, right? Remember, so the relationship is that, okay, so we have all the codes, right? And we have this singular code inside, right? And then inside would be uniquely decodable code, right? And then smallest set would be prefix code, right? So it's possible that the code is uniquely decodable, but it is also non-prefix code. Okay. Yeah, we'll give an example last lecture. If you forgot, just take a look. Okay, so here we just consider the more general case, right? We consider the uniquely decodable code, which may not be prefix. Okay, so yeah, let's see the theorem. Again, so this is a more general version of the Kraft inequality. Okay, probably the book has a different name. So, but yeah, if you see, just be careful on that. Okay, so the theorem is look like this. So we let C, the code, be a uniquely decodable code. Uniquely decodable, call that DRE code instead of the binary code, right? So now we consider a more general case, which means that the alphabet in Y has D element instead of just 0 and 1. Okay, it could have from 0 to D minus 1. Okay, DRE code. And then, so we can show the exact Kraft inequality will still hold. Okay, so basically in this case, it means that if we add for all the source symbols of length n, then we have D is the length of each code. If we do a summation of those, so it has to be less than or equal to 1, right? If we replace D by 2, then it will be the previous case. Okay, but that's only for the prefix code, right? Here we consider the uniquely decodable code. Okay, so yeah, which includes the prefix code. Okay, yeah. So okay, and this is the necessary condition, right? But this is also sufficient. Conversely, given a set of code lengths that satisfy this inequality, it is possible to construct a uniquely decodable code with this code length. Okay, so this is very intuitive, right? So it's basically, when D is 2 and when is a prefix code, then we can do that, right? So probably imagine it is not very hard to extend the case to the DRE code instead of 2RE code, right? Therefore, you may imagine that, okay, so if this is true, right, then how to construct code? Probably we can use the idea that we introduced for the prefix before, right? Because, so this formula is not different compared to the case of the prefix code. Therefore, we can just construct a prefix code to satisfy the condition, and then we're good, right? That makes sense? Okay, so yeah, so if it doesn't, it's okay. So because we're going to go through details of that anyway, so we'll see that later. Okay, so now let's try to prove it, right? To see how it works, right? So now it is not, so it may not be a prefix code anymore, right? So in order to show the necessary condition, so we can now use the code tree idea, right? So we need to do something else. Okay, so now let's see what we do here. Okay, proof. Okay, so what we do is kind of very tricky, right? So what we let this guy, the C power n, to be the nth extension code. Nth extension of C, and a code word Cn here is nothing but C1, C2, up to Cn, right? We concatenate them together. Okay, so now we can see that the length of Cn, so that equals to the summation of all the lengths of Ci, right? The length of all the code word. Yeah, I'll just use without bar here to make it our life easier. Okay, so this is the length of the code, right? Okay, great. So now let's see what we're going to do here. So yeah, we do the following manipulation. So what we do here is that we do a summation of this guy. Right, and this is more or less what we want, right? So basically, you see, so this is basically what we want, right? And so this is a bit different because it's extension, but we're going to see that how to reduce it to something like this. Okay, so let's see what we do here. So basically, the first step is that we're going to use this formula to expand this. So basically, here is the summation of all the lengths of all the codes here, okay, for the n extension code. Okay, and then after this, because now we have a d to the power of this guy, right? And if a summation here, and if we expand those, it will become a multiplication, right? So basically, we're going to expand this. So the first term would be d minus LC1, right? And then we multiply d minus LC2, and then minus LC3, and then go on. Then we have a minus LCN. Okay? Okay, so now let's see what is that. Okay, so basically, we consider all the possible code word here. Okay, so it's a sum over all the possible code word, right? And now we have a combination for all of them, right? So what, can you simplify this somehow, right? So basically, we have a lot of this like monomial term. Okay, in total, it's a polynomial, right? But each of them is a monomial, right? It's like this multiplication for different degrees. right? And then, but we have summation, so that's the sum over all the possible term, right? Can you tell me what that equals to? Like a simple version of it? Right, let me write it and see whether it makes sense to you or not. So basically, we can do this. So C in the C, right, and then D minus L C power n. Yeah, let's write it better. Does that make sense? Right, so if we expand this, so we're going to get it. Yeah, because it has all the possible combination there. Does that make sense? Right, it's like x plus y squared, right? And then you have all the possible combination of x and y. Right? Does that make sense? Yeah, hopefully it makes sense. But if it doesn't, then let's try a few cases, and you'll see that makes sense. Okay, so this is one trick that we do here, right? So this is equation 1. Okay, remember that. Then we can expand this guy in another way, right? So this is one way to expand it. So another way to expand it is that, so now we're going to try another expansion. Okay, so now we consider the same thing here. Okay, so another expansion. So here the expansion is just straightforward, right? We expand this using this formula, right? But for another expansion is that, so we're going to consider this as a whole, and then we're going to consider the code with the same length, and then add the corresponding term altogether. Let's see whether that makes sense or not. So basically what we do is that we're going to add I from 1 to n times L max, right? And L max is the maximum code length. Okay, the shortest code length would be 1, right? And the largest code length would be n times L max, right? Because we have n code words, and then the maximum length for each code word is L max, right? Okay, so now we're going to sum. Inside is for each code word with the same length, right? So now we're going to add over this such that the L of C would be equals to I, right? And then we can write D minus I here. Does that make sense? Right, so in this case, we just consider, we do a summation for each length of the code. Right? That makes sense? Does that make sense? Yeah.
So it's like for each, so we iterate through all the possible code lengths, and then
exactly.
the one is a sum of all the codes that
exactly.
that length.
Exactly.
Okay.
Exactly. Okay, so now we can have upper bound on that, right? So yeah, let's say for the code length, let's say for the code length I, so what is the maximum possibilities of the numbers of this length? I mean, the numbers of the code word of this length, right? For example, let's say here, this corresponding to the term that the code length is I, right? So what is the maximum of numbers of code word here? Right, length is I, right? And for each element, how many possibilities do we have?
You can have n code words per element, or per vector, right?
But for each element in the code, so how many possibilities do we have?
Is it D?
Exactly, D, right? Because this DRE, right? So the length is I, right? Then the total number, the maximum number of this code word would be what? D power I, right? So then we can have this. So basically, so now we don't need this summation anymore. Just replace it by D power I, because that's the maximum number of the code word of this length, right? And then times d minus I, right? The reason we can do this is that, so now we assume the code is uniquely decodable, which means it's a one-to-one code, right? Otherwise, we cannot do that, right? So because it's uniquely decodable. So this guy is non-singular. Okay. So yeah, if we have one to many or whatever, then that may not be true, right? Or many to one, that may not be true, right? But now it is uniquely decodable, it's singular, then we can do that, right? So we can see the summation, the multiplication of this guy is 1, right? So we know this equals to what? N times L max, right? Okay, so now we have another equation, inequality. So this is number 2, right? Number 1, we say this guy equal to this, right? Let's write it down. Okay, so basically now we use 1 and 2, see what we're going to get, right? Okay, so number 1 is that if we do a summation here, to the power of n, so this is number 1, and this would be less than what we get for number 2, right? So that's NL max. Right? Okay? And then from here, what we get is that we just do do the root n. Okay? Then we can get this guy would be less than n L max 1 over n. Okay, so now the important thing is that so this will hold for all n, right? So we do not have any assumption for n here, right? It will hold for all n. So this inequality will hold for all n, right? And clearly, when n goes to infinity, so this guy will decrease and it will converge to, right? So when n goes to infinity, so how to write it? Yeah, let's write it in this way. So when n goes to infinity, and this guy will goes to 1, right? So it's like n power of 1 over n, right? So how do you show that goes to 1? Yes, like n power of 1 over n, right? Limit n goes to infinity. Exactly. Take a log, right? Take a log. Yeah, and then the log will go to 0 because and it's monotonic increasing, then it goes. Okay, so yeah, that is how I do it, right? So this will goes to 1, very good, and then we can conclude that this guy will be less than or equal to 1. Yeah. Don't write the bar here. Okay, and we're done for the necessary condition. Right? Okay, great. And so this is a necessary condition. And for the sufficient, again, we need a construction. So again, so we're going to use a code tree idea, but code tree is not extremely straightforward. So we're going to see that later, okay? All right, so yeah, this is the proof, okay? And the one thing we want to emphasize here is that, so we mentioned that before. So know that there is no loss of optimality by restricting to prefix code. Right, so basically the code tree idea we got before is only for the prefix code, right? But now, since we have the exact formula for the prefix code and the uniquely decodable code, right? Then it means that if we use prefix code, so we do not lose any optimality. That makes sense, right? Therefore, so in practice, we normally use prefix code in this case. Okay, very good. So this is the Kraft inequality for the uniquely decodable code. Okay. So next, so let's see. So what is the necessary condition for the optimal code? Okay. So basically, this will give you a lower bound of the length of the code. Okay. So can I take a guess? What is that? Yeah, the average length of the code would be bigger than or equal to.
Just the entropy of it.
Yeah, the entropy, right? So that's what we do before, right? So remember how we showed that before? So we do some expansion for the entropy, right? And then we convert that to a mutual information, and then use the Funnels inequality to show that, right? A key in our proof is that, so we have to assume that the error will go to 0 when the n goes infinity, and also the error will go, error goes to 0, and when n goes infinity, right? So that's basically how we do it, right? So it means that, so it holds for the asymptotic 0 error, right? But now I want to show that, okay, so if we constrain ourselves to a 0 error, so that's still the lower bound. Okay, so which is not surprising, right? Because intuitively, if it holds for asymptotic error, now 0 error is a more strict condition, right? Right, okay. So let's see how we can prove that. So first, let's introduce the theorem. So consider a DMS. So consider a discrete memory source, meaning the distribution of each symbol is RID. The average normalized length of any NFG prefix code must satisfy this. So the average code length will be bigger than or equal to hx. Right? This is kind of obvious, right? So as we said, right? So here it's a more strict condition, right? Consider 0 error, and also we constrain ourselves to a block code. Okay. Yeah. Here, know that when we say ln here, we always consider block code. Okay. So this is notation for the block code. Okay. So now we have a few constraints here, right? Number 1 is a block code. Number 2, it is a prefix code. Okay. Number 3, it is 0 error code, right? Under all of these conditions, and then, so this is bigger than or equal to entropy. So which is pretty intuitive, right? Okay, but there's another thing that's not so intuitive. So which is, can that achieve the entropy exactly? Right, so that's the non-trivial part, okay? And this is what the proof I will show you will give us. Okay, so this will be with equality if and only if the probability distribution here equals to 2 power of minus L, the length of the code. Okay, so that's the condition when the equality will hold. Okay, you may imagine that, right? If the distribution of the source symbol is not that, then the equality will not hold. Okay, so we cannot exactly achieve it. So which is kind of also intuitive, right? Because this is what we can do without any constraint, and then let n goes to infinity. Right here, we consider a finite code length, right? N is finite, right? And then therefore we may not be able to achieve exactly this all the time. Okay, but we're going to show that we can, even if we cannot achieve that exactly all the time, we may be able to approximate that. Okay, and the loss is very minimal. Okay, so let's see how we can prove this theorem. All right, so the proof is like this. So basically, in order to show that, so this is larger than or equal to this, so we basically want to show the difference between this and that will be bigger than or equal to 0. Okay, so our goal is to show Ln minus n times the entropy. So this guy is bigger than or equal to 0, right? So that's our goal. And then let's see how we can show that. Any idea, by the way? So if you want to show something will be bigger than 0, then what do you think? Right? Did we learn anything like that? So did we introduce any quantity that will be bigger than or equal to 0? Yes, a lot, right? Entropy, KL divergence, or relative entropy, mutual information, they're all bigger than 0, right? So basically, now I want to kind of derive one of those kind of quantity, then we can say it's bigger than 0, okay? And also, another hint here is that, okay, with the equality if and only if this guy holds, right? And normally for all the, this quantity bigger than or equal to 0, we for all of them, we have a condition when the equality will hold. Okay, so that's another hint. Okay, so in this case, what we're going to derive is that we're going to derive the relative entropy. Okay, so we'll manipulate that to make it look like a relative entropy. Okay, let's see how we can do that. Right, the first step is that we're going to write it out, right? We're going to expand it. So for all x in the source symbol, okay, so yeah, just don't get confused here, right? So I think I use the same symbol here, right? So this n is the length of the source symbol, right? And before in our last proof, this n is the n extension code, right? So they're different. There's a k here, right? So yeah, but just don't get confused. Okay, so this is the definition for the Ln. Okay, and then we're going to expand the entropy here. Right. So yeah, that is should be minus. So that now we just because now the length is n, right? The length of the source symbol is n, right? We'll just write x equal to in that, and then we can write down the entropy, the n times the entropy equals to this guy. Right? We absorb n inside. Basically, it's the entropy of x power n. Right? They are IID, so we can write in this way. Right? So that's basically the definition of entropy. Okay. And next step is that basically we're going to take a minus sign out here. Okay. And then what we're going to do is that so what we're going to do is to try to write something look like the relative entropy. Okay, then we need this term look like similar to this term, right? So basically what we're going to do is that we take a log here, right? And then inside, because we have a log here, let's assume the log is based on 2, for example, right? So then I'll just write this, right? It holds for anything, right? Just use 2, for example, right? So for simplicity, we just let d equals to 2 in this case. Okay, or the entropy is based on 2, right? So entropy could be based on anything. All right, so that's basically how do we manipulate for this term. Okay, and then, all right, and then let's write the second term. So we have a minus sign here, minus sign there. So we can have a plus sign here. Okay, yeah, and this is what we got. Okay, next step is kind of tricky. So basically, yeah, for this kind of proof is based on experience, right? So if you do a lot of this kind of manipulation, you'll see this kind of makes sense, right? So basically what we're going to do is that we're going to add one term and then minus the same term here, right? And what term we're going to add, it's kind of related to this term, right? But it's a normalized, or it's a sum of all the possibility of this term, right? So basically what we're going to do is like this. So we're going to do a log sum over minus, let's use x prime here to differentiate between this x and this x. Oh, sorry, this x and this x, right? So we have x prime in all x. And okay, So you can see that the reason we want this kind of term is that, we have this term already, right? If we combine this term and this term, then we're going to have this term divided by this term, right? And that looks like a probability, right? It's a normalization term, basically. Okay, and then we're going to subtract this term. Px log sum 2 minus x prime in xn. Okay, so hopefully that makes sense to you. So we add this term and then minus this term, right? They're the same. Okay, and then we need to add our entropy term. Right, okay, so that makes sense. Okay, so next step is that, as we said before, so we're going to combine this term and that term. Right, so basically what we do is that we take out this minus sign, and then we have this minus that, right? You have this minus that, and then we combine that inside the log, becomes a division, right? So basically what we're going to do is that we take the minus sign out, and then we have our px here, and then log upstairs is this guy, right? And downstairs is this guy. Okay, so this is our the combination of the first two terms, right? And then we're gonna take this term here, add this entropy term. Okay, very good. And then we're going to subtract. So we didn't take care of this term yet, right? So we're going to write this term here. Okay, very good. Right, and now if we look at this term, the first two terms here, let's look at that term. What is that? So first of all, so this term looks like a probability, right? Right, we have one term here, and then downstairs summation of all the possibilities. Okay, so this one looks like probability. We have another probability, px here, right? So this is what? It's a KL divergence between P and Q, right? So, okay, then, so we have kind of like KL divergence, which is very good. Then we have additional term here, right? But the problem is that if this term matters a lot or no. Okay, so we have an important observation here. So, yeah, let's see. So what is that? So this guy. So does that look familiar? So is that what we just learned? Or it's not familiar at all? What is that?
Doesn't it have to be less than or equal to 1?
Exactly, the Kraft inequality, right? The Kraft inequality. Right, this guy is less than or equal to 1, right? So which means that it's inside the log, right? If inside the log is less than or equal to 1, then the whole term is bigger than or equal to 0, right? So the whole term is bigger than or equal to 0, okay? Therefore, we can have an inequality here. Okay, we'll have inequality here, and this will be bigger. So basically, we can ignore this term, right? We just let that to be 0, then we'll have a lower bound, right? Which is what we want. So remember that what we want is that we want to show this guy is bigger than or equal to 0, right? We need a lower bound. Okay, yeah, let's write it. So we have the first, yeah, let me introduce some notation to write it too many times. So yeah, let's assume this guy, as we said, right? So this guy is a probability, okay? So let's assume this equals to Qx. Okay, that equals to Qx, right? Then we can write the first term is this, Px log Qx, right? And the second term is our entropy term, right? Px log px. Okay, so we have an inequality here, and remember, so for this inequality, so when the equality holds, right? So if the Kraft inequality, the equality holds, right? So if this guy equals to 1, right, then the equality will hold, right? So this is a very important condition because later on we're going to see when the equality will hold. Okay, so that's very important. All right, so now we can see that clearly. So for this term, so we can write that in terms of a KL divergence, right? So basically, so it's basically like this term minus this term, right? So this minus that, right? So basically, what we're going to get is we have a px outside and log. Upstairs is px and downstairs qx, right? And this is clearly the KL divergence or the relative entropy between px and qx, right? So know that the order here matters, right? So p appear here and here, right? We can write, so it's not a distance metric, so we can, so the reverse is now true, right? So, okay, great. So now we get what we want, right? So now we can say clearly, so this is bigger than 0, and then we're done for the first part, right? So now we show that, so this guy is bigger than or equal to this guy, okay? So now the important thing is that to see when the equality will hold, okay? So this is the first condition, and then this is the second condition, okay? And for this guy, when the equality will hold, do you remember? Holds if, very good, px and qx, they are identical, right? Okay, then we can see, okay, so if both of them holds, right? So we say the equality holds if and only if, I mean for this and this, they're all if and only if relation, right? Sufficient and it's necessary and sufficient, okay? So two conditions. The first condition is that this guy equals to 1, right? The second condition is that px equals to qx, right? And we know what is qx, right? So qx equals to this guy over this, right? And we know that this, so it's 1, right? It's written here, so this equals to 1. Okay, therefore, the entire thing will just equal to 2 power minus L x, right? So we'll just say x here. We don't need to use x prime. There's no ambiguity. Okay, then we show, okay, so the condition is nothing but px equal to this. Then the equality will hold. Okay, and then we're done. Right, so this is a proof. Okay, so any question? Yeah, hopefully that will make sense to you. So, but it's a very harsh condition, right? So if px only equal to this, and then we can get the entropy, right? It's a pretty harsh condition. So what if it is not true? Right, think about that, right? So that's our next topic. So now we're going to see, so what is the bounds on the optimal length? Okay, let's see. So we're in the number 2 optimal code. Yeah, so this is not a new section, so we'll just write a bullet here. Okay. So we just showed that, right? So the optimal length requires that px equals to this. Okay. And if we manipulate it a little bit, then it can show that Lx will just equal to minus log px. Right, then that's log 1 over px. That looks familiar. right? What is that? Exactly, self-information, right? So this is like what we discussed in the beginning of our class, right? So intuitively, we just want to use this length to code. And now we show this is give you the optimal code length. Okay, but we're not there yet, right? So we need this guy, because L is a length, right? Then we need this guy. So this guy needs to be a integer, right? So if this guy is not an integer, then it's not feasible, right? It's a very harsh condition. Then what do we do, right? So if this is not an integer, then what do we do? Yeah, what is the number one you think about? Yes.
Use the next largest integer.
Exactly. We take a ceiling, or we take a ceiling, right? So basically, what we do is that we choose let's see the ceiling of it. Okay. So next question is that now we're not doing the optimal thing, right? We definitely lose a little bit, but how much do we lose? How much? Do we lose a lot? Right. The first observation we can see is that so this guy is less than or equal to this guy plus 1, right? And so does that look familiar? So if we do an expectation over that, right? Let's say now Ln equals to the expectation of Lx, right? Basically, that's let's say that's like this, minus, right? This. Okay, and what does that equal to? Right, the first term, this px times log 2 px with a minus sign, that will give you a, oh yeah, the minus sign is not here, right? So sorry for that. The minus sign should be inside. Need to be careful here. Minus log 2, right? So the first term, px times minus log px, so that will give you n times the entropy, right? And the second term, we use px, times 1 here, and then sum over all the px. So the sum over all the possible probability here, right? So that will just give you a 1. Right? Therefore, so we can get very interesting result. Ln would be less than or, oh yeah, this here should be less than or equal to, right? Would be less than or equal to n times hx plus 1, right? And we got a lower bound of this already, right? So remember that, so we have a lower bound on this already. So we have our theorem before. So using our theorem, so which is this one, our theorem star, okay? Using theorem star, and then we can see that this guy is bigger than or equal to this, and less than or equal to this. Okay, and then if we normalize it, we can have the average code length equal to this, less than or equal to this, and bigger than or equal to this. Okay. So basically, you can see that if we just do this, so we're not losing too much, right? So on average, we just lose a little bit, 1 over n, right? When n becomes very large, then we're good. Okay. Any questions? Oh, I have 1 minute left. Okay, so yeah, let me just introduce a little bit here. Okay, so as we said, I don't know, what should I say? Yeah, so it's almost 40. Yeah, maybe I'll say the next lecture. Okay, so we'll give a name of the code. Maybe I can give the name now. So, if we do this kind of thing, right, we use this formula. To do our encoding, okay, and also including this case, right? So this code is called Shannon code. Okay, so this is the first practical code we learned. Okay, so we're going to study how to construct the Shannon code if the length is given. Okay, in the next lecture. All right. Okay, thank you.